Now we'll take up a good problem on Gauss Law. There is an uncharged hollow metallic sphere. So this is an uncharged hollow metallic sphere. This is of radius chota a. And a charge Q plus Q is placed at the center of this hollow metallic sphere. Now we have to find first part, the surface charge density on the inner and outer surface. So that's why I have drawn this slightly thick. Actually it's not very thick, but we have drawn it slightly thick so that we can see the inner and outer surface. So basically we want to find out what is the surface charge density, that means the charge per unit area on the inner and outer surface. So to solve this question, we can draw a Gaussian surface here inside that metal. So this is our Gaussian surface. So Gaussian surface is a spherical surface just inside that metal, okay, that metal that is making up this hollow metallic sphere. Now this metal, inside the metal, everywhere electric field is zero. If electric field is zero everywhere, then electric flux is zero. If electric flux is zero, Q enclosed will be zero. If a charge chota q has come on the inner surface, then the charge inside this is zero. Inside this Gaussian surface, that means this q plus this q should be equal to 0. Therefore, the charge on the inner surface turns out to be minus q. And this is an uncharged metallic sphere. Therefore, the net charge on it must be 0. If minus q has come on the inner surface, plus q must come on the outer surface. So this is a very important result. If a hollow metallic sphere is there and we keep a charge plus q at the center, in fact we can keep it anywhere inside, then minus q charge comes on the inner surface and plus q charge comes on the outer surface. All excess charge goes to the outer surface. So we can think of it as this way. This plus q basically pulls minus q on the inner surface and the remaining charge goes to the outer surface. The reason for that, as we have understood, if you draw a Gaussian surface inside this metal, everywhere electric field is 0. If electric field is 0, electric flux is 0. If electric flux is 0, charge enclosed will be 0. Plus q is anyway there. So minus q has to come in here so that inside this the net charge is 0. Therefore, the charge per unit area on the inner surface will be equal to minus q by the surface area of this sphere, okay, inner and outer almost same here, so by 4 pi a square, that is the surface area. And the surface charge density on the outer surface will be plus q divided by 4 pi a square. Now, the second part of this question is, now this is not uncharged hollow metallic sphere, it is having a charge plus small q on its own. So, this is now a hollow metallic sphere, there is a charge plus capital Q at the center, and now this is also having a charge plus small q. If this is what is there, then this plus q will anyway pull minus q on the inner surface because of the concept we discussed in the previous part, and all the excess charge will go to the outer surface. Excess is plus q that is there on this plus this q. So basically now what happens, when this was originally having a charge plus small q, then this does not change because this plus q will pull minus q inside, so that the charge inside this Gaussian surface is 0. All the excess charge will go to the outer surface, so plus q will also go to the outer surface. Net charge on this hollow metallic sphere is now plus small q, and this is how the charge gets distributed. The charge on the inner surface will not change, charge on the outer surface will change. Therefore the charge per unit area on this outer surface, we can call it OS. Okay, outer surface will be now q plus q divided by the surface area 4 pi a square. Now there is a third part to this question, and they want us to calculate the electric field at a distance x from the center, okay, in both the cases, okay, and x is less than a. So now this point is somewhere here, so we can draw a Gaussian surface here, okay. All symmetry arguments will hold. The electric field will have the same magnitude on this, at every point on this Gaussian surface. Electric field and dA vector will be parallel at every point. So the electric flux will simplify to E into A, and this is equal to Q enclosed by epsilon naught, Gauss law. Here area is the surface area of this Gaussian surface. So E into 4 pi x square is the surface area. Q enclosed is this Q only. All outside thing don't come into picture. So just Q here by epsilon naught. Therefore electric field will be 1 by 4 pi epsilon naught Q by x square in both the cases, because in both the cases the charge enclosed by that Gaussian surface is Q plus Q. What is happening here does not make any difference.